All right, great. So we're here today to talk about the effectiveness of highway bioswales in treating stormwater runoff in Maryland. Our speaker today is Dr. Keith Eshelman. Dr. Eshelman is actually a professor at the University of Maryland Center for Environmental Science and is based at the Appalachian Laboratory in Frostburg, Maryland. His research interests are in the areas of watershed and wetland hydrology, groundwater and surface water interactions, biochemical processes in upland and wetland ecosystems, water quality modeling, and ecosystem responses due to natural disturbances, energy development, and land use. His field-oriented research programs has focused on man's impacts on the hydrologic cycle, specifically on examination of the hydrological effects of acid deposition, forest disturbances, surface mining, shale gas development, urban stormwater management, and peatland drainage and restoration. We're really excited to have Keith here, and we're really excited to see what his research has brought about this long-term research that he's been doing in Maryland. So with that, I'm actually going to turn it over to Keith. So Keith, I'm going to go ahead and stop sharing my screen. If you want to go ahead and share yours. Perfect.
Okay, thank you, Missy. You can hear me okay, correct? Okay, I see the thumbs up. That's all I need to see. So, okay, well, welcome everybody. Good afternoon. I'm very happy to be here, and thank you, CSN, for the invitation to present today. As Missy said, I'm going to be talking today about the effectiveness of highway bioswales in treating runoff from impervious surfaces along Maryland highways. This is a long-term project that began back in the teens, back in the 2013 era. Went through this year actually with funding from different folks. And this is probably honestly the hardest project logistically that I've ever had to do. And I think as you'll see, you'll understand why. The idea of collecting environmental data in the median of active highways across a fairly urban state is something that's not for the faint of heart, quite honestly. Okay, so I'm going to roll on here. My director, given the times as they are, sort of asked me to put this somewhat shameless plug in for our laboratory, in case you're not familiar with us. We're the Appalachian Laboratory. We're located in Frostburg, Maryland, and we're part of UMCES, or UMCES, which we think of as Maryland's University for the Environment. Here's the picture of our beautiful building right off of Interstate 68 out here in Western Maryland. In Allegheny County, by the way. The lab is about 40 people, 40 employees, including 14 faculty, other research staff, administrative staff, and so on, plus about 15 graduate students. Our mission is to advance scientific knowledge, train the next generation, and engage stakeholders like the stormwater professionals that I'm assuming are logged into today's call. And you can check us out at the website if you are interested. I'm going to just use that as a jump off for the acknowledgments. I'm going to acknowledge right off the bat UMCES, particularly the taxpayers of Mary's Land, as our former president of the center, Don Bosch, used to call it. Acknowledge support from Maryland State Highway Administration, Highway Hydraulics and Water Programs Divisions, and the U.S. Department of Transportation Federal Aid Highway Program, and our most recent sponsors, the Chesapeake Bay Trust Restoration Research Program since 2002. My collaborators are Emeritus Professor Ray Morgan, also from AL, and Katie Klein, our person who did much of the work on the water quality and soils for this particular project. And then, as always, there's so many people that gave of their time and energy in terms of laboratory assistance and field support that were absolutely critical in getting the job done. Okay, I don't think I have to spend 5 seconds, honestly, on this slide, given the people that are likely here in the audience. We all know that stormwater is an important issue for the Chesapeake Bay restoration, and I think we all realize now, thanks to, honestly, the folks some of our ecology brethren, honestly, who really worked on the urban stream syndrome issue, realizing the problems of traditional stormwater management practices, or gray infrastructure, if you want to think of it that way. So what I'm going to be talking about today is green infrastructure, particularly swales. And of course, what are swales and their functions? These are really just engineered ditches that their primary function is to convey stormwater while allowing for both abstraction, which I think of as a hydrologist as permanent storage or loss, and detention or transient storage. Now, abstraction from a swale would result from soil infiltration and the loss of that infiltrated water either to evapotranspiration, returning it back to the atmosphere, or going down the other way and recharging groundwater. But in either case, we're dealing with a reduction in runoff volume, if you want to think of it that way. Detention, on the other hand, this transient storage, would be presumably enhanced by channel roughness, grassy vegetation, check dams, anything that sort of provides resistance to water flowing through this conveyance. And these things, of course, would result in attenuation of the storm flow runoff hydrograph. In addition, we're thinking that swales could also be useful, and there's some evidence to this, that we might see reductions in pollutant concentrations and loads. So today I'm going to be talking about half about hydrology, this abstraction and detention function, and then I'll be spending about half of the time at the end of the talk talking about water quality, the latter issue here. So what's a bioswale then? You probably know it's a swale in which we've replaced the native soil with layers of quote unquote bioretentive soil, sand, and layers of aggregate that enhance soil infiltration and hopefully cause a increase in pollutant retention. Underdrains are often used to maximize infiltration in these systems, and bioswales have been widely used by the State Highway Administration to address their NPDES MS4 permitting issues. And I have here reduced pollution to the maximum extent practicable, or MEP, which I'm sure you've heard about ad nauseum. Okay, so here's the schematic of the bioswales that we worked on. Here's their diagram. So what do we see? These things are about 8 feet wide maximum, okay? Variable lengths determined by the size of the mini catchment, the amount of impervious surface, basically. We have layers about 12 inches minimum of bioretentive soil, planted with vegetation, of course, and then underlying that layer of bioretentive soil, which is, by the way, mostly sand and organic matter, we have layers of pure coarse sand and multiple layers of aggregate. Okay, and then located within that lowest level of aggregate is going to be a 6-inch perforated pipe, which is used then to collect water percolating down through the soil into the aggregate and route that via gravity flow to an existing stormwater inlet. Now, all the bioswales that we looked at, they were all examples where the inlet was already in place, it was existing, and these were essentially retrofits or conversions. So a hole had to actually be cut in the concrete wall of the inlet to receive this drainage pipe. So this is all below ground now, right? Below the land surface. And then you see some other details, some check dams here that are really only used in steep bioswales. Okay, so our objective then, what was it? Well, we wanted to assess the effectiveness of bioswales in achieving stormwater management goals through multi-site, paired, field-scale comparisons of storm flow responses. And the comparison is going to be with nearby grassed swales that served as controls. Okay, and to do that, we instrumented pairs of highway swale mini catchments across the state of Maryland. Several in Washington County, in Hagerstown along the dual highway. Those were discontinued after 2016, and we moved our operation east to Howard County on US Route 40 in Ellicott City, and also to Frederick County along US Route 14 north of Frederick near Lewistown, if you know where that is. There's no pretreatment calibration data here. It's just a paired comparison of responses to paired events. The paired swales, as we'll see, have similar areas, slopes, and imperviousness. And again, I already said the performance will be assessed relative to the grass swale control. And here's one of our instrumented bioswales. This is our delta swale. Apologies for the sort of the unoriginal naming of these, but this was delta. And you see the flume used to collect overland runoff. You see some along the sides here. We have some wing walls to channel the overland flow through the flume. We have an instrument shelter that houses our ISCO samplers, our sequential samplers. You see some wiring here, which goes to our ultrasonic level sensors, one inside the flume and one down actually at the underdrain. Believe it or not, you can't see what we're doing down there, but trust me, we have a stilling well and an ultrasonic sensor and an intake for our underdrain sampler as well. And then there's a tipping bucket and a solar panel that's not shown in the photo. Here's our controlled grass swale further down the highway toward Ellicott City. So the methodology, we're doing chemical and physical characterization of the swale soils, including infiltration capacity. We did continuous rainfall monitoring with tipping bucket gauges. We have continuous gauging of both overland flow and underdrain runoff, 5-minute data with the sensors and the rating curves that we had to create. We did automated sequential sampling for a subset of the storm flow producing events. This is 3-season work, March through October. We then took everything back to the lab and did laboratory analysis for a variety of dissolved and suspended constituents, 25 different ones actually, including the classic ones, nitrogen, phosphorus, suspended solids, trace metals, major ions, etc. And then we took all those data and crunched them, and we computed and statistically compared paired event runoff depths, runoff ratios, peak runoff rates, and discharge weighted event mean concentrations and loads. A lot of samples went into this and a lot of data. So it's heavy on data, and that's why I'm going to try to move through this as quickly as I can. And then just sort of in passing, almost new in 23, 24, we did synoptic swale stormwater sampling to try to assess the variability in swales across the sort of a population of swales along a highway corridor. And I think I have one slide to show that. Okay, so just quickly, design issues. The paired design, this is going to be weird for some of you because you're thinking, if you go to this trouble, why not do an input-output study? Well, if you think about it, this would not be the place to do an input-output study because the inputs of water to these highway swales is so diffuse. We could have everything from direct rainfall onto the swale to water coming in at the head of the swale to water going in as overland runoff from the highway surface all along these individual bioswales. So that's just not tractable in my mind to do. So we're doing a paired comparison with the idea that we should be able to see a difference between the two, to see whether these bioswales are any more or less effective in achieving stormwater goals than the grass swales. Now, a word about the grass swales. These are not the grass swales that were designed according to MDOT State Highway Administration standards for approved grass swales. That would be ESD M8, okay? These were not those. In fact, State Highway considers our grass swales to be abandoned. These were built during when the highways were constructed back in probably the 1940s and 50s. So they're old, they're abandoned. They don't meet SHA modern standards. So any differences we see between the bioswales and the controls, we consider to be a maximum difference. We would presume that the approved grass swales would do better than these abandoned ones. And then I'm going to just gloss over this. We were unable for logistical reasons to instrument the Kappa swale, the control grass swale in Ellicott City, which is 5 kilometers east of the bioswales, by the way. We couldn't do that until the beginning of the 2020 field season, and this meant we had incomplete data on rainfall coming into this mini catchment. So we had to use NEXRAD level 3 5-minute rainfall data based on the Sterling, Virginia radar to estimate rainfall for these events that occurred prior to the 2020 field season. This was just for safety, by the way. They didn't even want us out there at all. We said we have to get out and get something. We did get something. We got a lot, but we weren't able to permanently locate this equipment. So we did a duration here, and the good news is we did a validation of this approach to using NEXRAD radar rainfall data, and it really worked out quite well. We see that we've taken all the bias, virtually all the bias out of the rainfall estimate, so we feel really good about what we have here. But I just wanted to make sure you understand how we did that for that earlier data set. Okay, so here are our study sites. The Delta bioswale, about an acre, 45% impervious. Bioretention area is 0.04 acres. And you see where the bioretention is. It's down here at near the outlet, closest to the outlet of the mini catchment. Okay, these don't fill up the entire swale. In fact, the upper portion of the swale looks exactly like a grass swale without the bioretention. And then here's Kappa down here at the bottom, similar catchment area. Imperviousness is a little higher, but obviously no bioretention. And then this is our Omega bioswale at Ellicott City, a little larger. Here's our Epsilon swale up at Lewistown, and then our Zeta grass swale at Lewistown as well. And by the way, as we roll through this, if you're not good with the Greek alphabet, just remember if you're seeing green points or green text here, a green background, that's the bioswale. If you're seeing brown, that's the grass swale. And don't say, why did you do it that way? Grass is green. We know that. We think of the bioswale as a greener component of stormwater infrastructure. So this is the green bioswale, brown is the grass swale. Okay, here are our synoptic stations. Just the notion, here's where the exit is for Route 40 at Ellicott City, if you know this, off of the Interstate 70, and you see all this population of grass swales and bioswales going all the way down here to the interchange with US Route 29. This is what we tried to deal with when we did our synoptic work, and I'll come back to that. So when I say synoptic, I mean, as it says here, as we use it in meteorology, relating to data obtained nearly simultaneously over a large portion of the atmosphere. In this case, collecting samples over a large portion of the storm water response along a highway corridor. Okay, this is the only hydrograph I'm going to show. Trust me, I picked this one. It's a nice one. This was data from Tropical Storm Ophelia, if you remember that, about 2 years ago in September. It's a long event, about a 2-day event, honestly, with 2 big pulses of rainfall coming through. And here are the responses to the Kappa swale, the Delta bioswale, and the Omega bioswale to this event. You see it was about a 5.6 or 5.3 centimeters of rainfall, variable runoff R. And you see that there are some differences. One thing is different is notice that the discharge in none of these swales occurred instantaneously with the first drop of rain. It took, in this case, at least about 8 hours for the Kappa grass swale to respond. Same for the Delta bioswale. And you see, if you look down at Omega, the response didn't happen actually until the next day. So there was clearly a large abstraction of water at Omega that we're not seeing at Kappa and Delta. Something else in common, you're seeing that the peak response here that occurred on the second day at all 3 swales, very similar, somewhere between 100 and 150 GPM, gallons per minute at the peak. So not a big difference, honestly. And you see one other thing, you see Kappa actually stopped flowing for some periods. It became intermittent, whereas you see at Delta, once the thing started flowing, it's flowed throughout about, about 38 hours or so through that particular event. So some differences, some similarities, but we're going to try now to take all the data from all the events and make sense of it. So before I do that, let's just show the data on infiltration capacity. We carted a lot of water out to these swales over about 8 years doing double ring infiltrometer tests. And long story short, what we basically found was that the steady state infiltration capacity for water into the swale, the biosoil itself, is 5 to 10 times higher than what it is into the other highway median or grass swale soil. So that was statistically significant at the 0.5 level, but we didn't find any statistically significant among site differences. But this graph clearly indicates this is a big difference, right? This is a sandbox, for lack of a better word. Okay, so let's get into it then. So what did we see hydrologically? And I'm checking my watch, about 25 after, so I'm right on track here, I think. We saw dramatic evidence of dramatic overland runoff reduction in the bioswales. So what these bioswales did in the 3 pairs that we looked at was reduce overland runoff by 87 to 99%, basically. Universal response, and you see here in the table that the runoff, the overland runoff over 150 storms at Delta was only 27 centimeters, whereas over at the Kappa grass-swale, we had over 200 centimeters during the 8 years that we worked at those sites. Omega, only 3.5 centimeters of overland runoff was ever discharged, 6.1 at Epsilon. So you see that this is dramatic, isn't it? I mean, this is what these things were built to do: get the water largely into the bioretention system. And it did that for all but a small portion of the total overland or total storm runoff. How did it do then for runoff reduction, this volumetric reduction? Well, not as well. And when we look at all the data, we see some mixed responses. And for all the data, 157 storms at our Delta and Kappa swales, we found no significant difference over the 8-year study. But then when we looked at the event rainfall for these same 157 events, we actually found that there was a difference, that the Delta swale received about 11% less rainfall than did Kappa. So it probably makes this difference, if anything, a little smaller than what it should be. In fact, it's likely that if these swales had been located contiguously, that we would have actually seen perhaps greater runoff from Delta than from Kappa. At Omega versus Kappa, however, we see more evidence of a runoff reduction in the bioswale, statistically significant, minus 30%. No significant difference in rainfall, however. And at Zeta Epsilon comparison, we see the exact opposite, about plus 70 or so percent increase, statistically significant in combined runoff from the Epsilon bioswale compared to Zeta. So the next thing we did was say, wait a minute, with all this variability in rainfall, let's try to narrow that down. And while we're doing it, let's just look at the smaller rainfall events, the ones that are less than an inch of rainfall. And when we did that, the data become a little bit neater, a little cleaner. Now we see that the reduction in volume runoff at Delta is about 21%, actually goes up to 80% at Omega, and comes way down to plus 25 or so percent at the Epsilon site. And now the differences in rainfall in Ellicott City are almost totally go away, 7 and 10% respectively. So we think here now, our interpretation of this, honestly, is that there's probably a slight reduction at Delta, probably a pretty good sized reduction at Omega, and if anything, maybe Epsilon, nothing at all, or maybe even a little bit of an increase, but we'll come back to that. In terms of runoff coefficient, obviously, when you divide a number that has some error by another number that has some error, we tend to magnify the differences, and that's what we see with runoff coefficient. So we found no difference significantly at Delta versus Kappa. Omega versus Kappa, a reduction of 47%, however, and then we're still up here in the plus 70% at Epsilon. And I just want to point out here off to the right, all of these events where we ended up with a runoff coefficient greater than 1. So something truly does seem to be askew here, and we're thinking underestimation of mini catchment area, or perhaps some systematic underdrain gauging error. We don't know exactly what's going on there, but we're working on it. Seasonal runoff reduction, we're also seeing this happening. And basically the bottom line here is that underdrain runoff becomes the dominant source of runoff or dominant component of runoff at the bioswales, 87 to 96%. To a first approximation, that reduction in overland runoff is simply counterbalanced by this dramatic increase in under drainage. And I just want to show here that this is evidence that we're doing things the right way. This isn't garbage in, garbage out. We calculated runoff coefficients seasonally, and I compared them with a calculation I made of a runoff coefficient, a long-term seasonal coefficient for the Little Patuxent River at Guilford, within which two of these mini catchments, or I'm sorry, three of the mini catchments are located, and we got a value of 0.365, which agrees very nicely what we got at Kappa and at Delta. In particular, the values from the other swales are somewhat different. So we feel like we're very close here to having the true numbers, still trying to figure out what's going on at epsilon, but we do feel like there's strong evidence here for volumetric reduction at the omega bioswale, but much less, if any, reduction at the delta site. Okay, I want to emphasize one point quickly. When we think about, again, a long-term study like this, one of the things we can do is look at what kind of events are producing storm flow and overland flow. And what we found is something I think that we often forget in this business, which is when we look at events with rainfall less than an inch and greater than 1 inch, it's really those greater than 1 inch events that are responsible for the lion's share of stormwater runoff from these swales, right? So in this case, we're seeing 75 to 80% of the total runoff coming from these larger, less frequent events, honestly, whereas these sort of run-of-the-mill events with less than an inch of runoff are really kind of small potatoes. And it's even more dramatic when we look at overland flow from our bioswales, as I said. Now, and this is data from Delta and Kappa, but same kind of thing we see from our other pairs. We see we're up now to 95% when we look at overland flow. It's even more dramatic. So really, as we think about the future and what climate might look like in terms of increasing the intensity of rainfall, this is something we should be concerned about, because this is likely to just be magnified as we move into the future. And then just a few slides on runoff attenuation. So here we're looking now at that detention function. We saw some evidence, well, it's statistically significant, about 20% reduction at delta relative to kappa. Nothing at omega, however. Remember, this is the big volumetric reduction station. Nothing significant when we look at the peak and its attenuative capacity. And then epsilon is still behaving kind of crazily compared to zeta. And I don't think I have to get into it, but again, as we saw with the event rainfall depths, we see the same thing here with maximum hourly rainfall intensity. We're seeing that there is a difference, in fact, spatially between delta and kappa. So perhaps some of this difference in runoff attenuation is really an artifact of the fact that the intensity out at the bioswale was less than at the grassed-swale. And then something about timing. Timing would come into play if we're detaining too, right? If we're detaining, we would expect this thing to be shifted, right? We might delay that peak in time. We don't see any of that from any of the sites. This is our delta kappa comparison. The median, I think 121 events, the median was exactly 0 hours. This is the centroid of the runoff volume, okay? If I look at the difference in the centroid of the runoff volumes, delta and kappa paired now, each one's paired, every event's paired, nothing. We can't even get 5 minutes. The median difference from omega and kappa was 5 minutes, 0.08 hours. So not much evidence here of a change in timing associated with the bioswale. Okay, let's move. I'm right on track. God, I can't believe it. I'm right on track here to hit the water quality. So the first thing we saw when we started comparing the samples that we collected, and by the way, these aren't individual samples, these are discharge weighted EMCs. Everything you're seeing here is a storm event EMC, an event mean concentration, all flow weighted, typically 12 to maybe 20 samples, some cases less, where we only got 4 or 5, but in most cases we're dealing with a significant number of samples in each EMC. And here we have, as I see down here at the bottom, we have a large number of those. We have 18 flume events and 48 underdrain events. And what did we see? Well, we saw for almost every constituent, almost, not quite all, we saw for the most of the constituents, we found that the EMCs in the underdrainage were much, much higher than they are in the flume runoff. Okay, so higher underground, less flowing across the surface. And of course, you might think, well, that's not really that earth shattering. That's just due to the interaction of that percolating water down through those materials with those materials. And I think that is the mechanism. We see greater soil water interaction in the under drainage than we do through the overland runoff. So for example, for specific conductance, SC, it's about 3 times higher in the under drainage, the acid neutralizing capacity almost 4 times higher, sodium concentrations factor of 5, sulfate factor of 5. Get down here into the nitrogens. Look at this nitrogen. We're going to come back to this. 1.4 versus 3 for total nitrogen. Nitrate, 0.1 versus 1. So a 10-fold increase in nitrogen under drain versus flume. It's really only when we get into phosphorus that we see the opposite applying. TDP, total dissolved phosphorus, was 0.31 in the flume, 0.13 in the under drainage. That's not a typo. That's the real number. Total phosphorus, 0.4 versus 0.18. Phosphate, ortho-P, 0.27, 0.06. So we're seeing reductions in phosphate EMCs and phosphorus EMCs through the under drainage process compared to the flume. And then trace metals, we're seeing some of the same problems as for nitrate. We're seeing big increases in concentrations in the under drainage. Okay, so this means as I move forward now, we're going to be looking at combined runoff, grassed swale versus bioswale. So when we combine the runoff from the flume with the runoff from the underdrain. Everybody's following me. I have 2 mechanisms in the bioswale, 2 pathways, and to get the combined runoff, EMC, if you will, I have to combine those 2. We do that, we runoff weight those 2 individual components. Okay, so that's where we're going now. If this thing works, there it is. So let's look at phosphorus first. This is where the bioswales truly shine with respect to phosphorus. And you see right off the bat, these are all our 3 comparisons here. So we're looking at phosphorus in milligrams per liter. Anything colored in here, solid colors, are statistically significant. If it's an open bar, it is not. So we see a lot significant here, delta versus kappa. And what do we see? The bioswale is bringing down those phosphorus concentrations, isn't it? We see the same thing up here at epsilon versus zeta, bringing it down. We see the same thing at omega, but we have fewer events, only 20 events to work with. So we see it for ortho-P, we see it for TDP and TP, but it's not statistically significant. So we need more data here to really get a universal response. But for ortho-P, at least, we find the dominant form of phosphorus runoff in all 5 swales is ortho-P, and we see significant reductions of the order of 35 to 85 or so % at the bioswales. And we're going to talk about this as being due to sorption of ortho-P onto soil, iron, and aluminum oxides. That's our kind of our working hypothesis moving forward. We also found reductions in TDP and TP EMCs. Here are the loads. I'm not going to spend much time on it just in the interest of time. This may not even be a great way to display it. But on the left here, we have ortho-P and TP, all the events. And then on the right, the 2 slides are for events with runoff less. Is that runoff less than an inch? Yeah, runoff less than an inch. And all I'd say here, if you look at this, you eyeball at this and say, I don't really see the difference. There is a difference. Trust me on that. And the way I like to look at it, if you look at these slides, the outliers, the real high values for phosphorus are typically brown dots, aren't they? They're either brown open circles or brown solid circles, kappa versus zeta. And those are typically the ones that are high, the grass swales. Whereas the bioswales, with the exception of few flyers here, tend to be very low, tend to be less than maybe 0.05 kilograms per hectare. So a lot of strong evidence here that not only is the EMC down, but the loads of these constituents are coming down as well. For nitrogen, the exact opposite. This is not a good story. So what we're seeing, instead of a reduction in nitrogen, nitrate, for example, dissolved organic nitrogen, total nitrogen, total dissolved nitrogen. We're not seeing that at all. In fact, we're seeing that the bioswales are a source, and we're seeing that the EMCs for nitrate, for example, were higher than a factor of 3 to 7 compared to the grass swale. And we think this is due to the flushing of microbially mineralized and nitrified nitrogen from the bioswale, through the biosoil into the underdrain and out of the mini catchment. That's what we think is going on here, but that's maybe more of a hypothesis than anything. Here are the event loads, same as we looked at for phosphorus. The outliers, the flyers here are all green, right? Those are the bioswales. Typically, those are green. The brown dots are all very low, down, like I said, less than maybe 0.1, 0.05 kilograms per hectare. The flyers here are green, showing again just what I talked about, that these things are likely sources of nitrogen. And then for a few other constituents, we're dealing here with our major ions. I'd like to point out a difference here that isn't significant, and it's a good thing. I'm looking at chloride here, the second to the last bar on the right. In each case, we see no significant difference between the bioswale and its paired grass swale control. That's a good thing. In hydrology, we often use chloride as an inert, non-reactive tracer, right? And to see the fact that these pairs that we selected are producing similar EMCs of chloride is a blessing. And it's a testament and a validation of the hydrologic gauging that we use on which our conclusions are ultimately based. So that's a good thing. We're not seeing any difference in chloride. Otherwise, we'd be thinking, wow, we might have a problem, Houston, we might have to look into. We're not seeing that. Rather, we are seeing, though, that these bioswales are sources of things like sodium, of calcium. Well, these are limestone aggregate within the underdrain, so no surprise there. Sulfate can weather out. So there's evidence that these things are active. There's something going on here in terms of mineral-water interaction, but it's not for chloride. Okay, so that's cool. And then the other pollutants, surprisingly, you probably thought these bioretentions would be great filters of suspended matter. Turns out they're not. We found no evidence of any reduction in TSM. The one place we found a significant difference was actually the opposite. Omega actually produces more TSM, higher EMCs, than does Kappa. The other ones are not significant. And then one thing that is significant and not to our liking is the enhanced leaching of trace metals that we see through all these biosoils, namely that copper and zinc and so on, the concentrations at all these sites are statistically significant and higher in the underdrain runoff. Okay, let's wrap that. Oh, so what could be explaining? Let me just check my watch here. We're running pretty long here. We think there's something else going on here, and we're worried about the damage and modification of the underdrain cleanout. So there's a cleanout here that's supposedly fitted with a watertight cap. When we first looked at all these sites, we found lots of caps that were laying around, had been damaged, maybe hit by mowers, et cetera, et cetera. And then we found some where the downpipe was actually splintered off, as up here at the left. But this is the one that really troubled us. Down here at the lower left, this is from our Omega bioswale that we found this about a year ago, well into our second project. And here somebody had either intentionally or maliciously or for reasons that we're not sure, cut a hole in the cap to allow for the preferential drainage of this bioswale through the cleanout, which one of my assistants called not bypassing, but biopassing. It's bypassing of a bioswale, okay, because it's allowing that water to go directly into the underdrain rather than having to percolate through the median. So this is a potential problem and something that I think we need to be thinking about. In the interest of time, I'm not going to talk about this slide. I'm putting it here. I'm just going to mention one thing. We found almost uncanny agreement between our synoptic EMCs that we computed based on a synoptic survey. You should have been there for this. A synoptic survey, we walked that entire highway corridor and took grab samples all along the way and then compared them with our EMCs that we calculated for the same event for our grass swale and bioswales. It's really unbelievable. If you work down through this table, go back and look at it, it's almost somebody, you can't make this up. It's so good agreement that there's something here. It's a whole paper we can write just about this synoptic survey, which I don't know anybody has ever done. So it's really novel. Okay, I'm going to skip. I think I better skip this, Missy. Honestly, we're running late, and okay, let me just say quickly. Nitrogen, we did soils characterization. We measured nitrogen, total nitrogen, nitrate, and ammonia in the soil itself. And back up, we found the higher nitrate coming out and the higher total nitrogen coming out of the biosoils, right? Bioswales. So the expectation from the stormwater work is we ought to see higher nitrate, ammonia, and TN concentrations in the soil itself. If you're seeing more coming out, kind of would make sense that maybe we would see higher concentrations in the soil. Well, we don't see that. The bottom line is we don't see that. If anything, they're the same. Maybe for total nitrogen, the bioswale is actually showing lower concentrations at all the levels. And this is 0 to 5, 5 to 10, and 10 to 15 centimeters. So there's no evidence here of any lower nitrogen concentrations in the soil, which sort of gets back to this idea what I mentioned before. The source of nitrogen is not related to the actual ultimate source, the amount of material there. Rather, it's due to the continuous interaction, the leaching, if you will, of water through the profile and the extraction of these nitrogen components and subsequent discharge through the underdrain. That, I believe, is the mechanism, not the one that I mentioned earlier. And then for trace metals, same deal. Why wouldn't we see higher concentrations in the biosoil? We don't see that. If anything, it's lower, maybe the same, but nothing like we saw tenfold changes in copper or zinc. We don't see anything like that here. Look at chromium, very, very low, but yet we saw the enhanced leaching through the biosoil. And then similarly for phosphorus, but kind of in reverse, if we saw less phosphorus coming out, right, maybe you could make the point that maybe there's less in the soil. Well, actually, it's the opposite. Maybe thankfully, when we do a MELEC3 phosphate extraction, what we find is there is a significantly higher concentration of ortho-P in the biosoils themselves compared to the grassed-swale and the median soils. And it's not until we look at the P150 values where we don't see a big difference, but the combination of these two things where we calculate the degree of phosphorus saturation, now we do get a significant difference. So if we just looked at a P150, we couldn't see what's going on here. But when we combine it with our MELEC3 extraction, we see now that the phosphorus saturation in these levels is much higher in the biosoil compared to the median and the grass-swale soils, right? Because that's what this thing is doing. It's basically chemically sorbing ortho-P onto these soil materials within the bioretention area. Okay, 3 more slides, Misty. I see you there. Thank you for the 5-minute warning. Boy, if you watched that Maryland women's game last night, how many 5-minute warnings were there? If anybody stayed up to watch that, I did. I've never seen a basketball game like that in years. And the men's game was unbelievable. So for Maryland, these are good times to be a basketball fan, right? Okay, that was a aside if there ever was one. Okay, so did the bioswales achieve the design objectives for ESD in Maryland? So here we got to go back to the stormwater manual, and there's 3 questions. The first one, the first standard is, did we capture and treat 90% of the average annual rainfall? Here's my calculation. It's the rainfall minus the flume runoff, which wasn't treated, divided by the rainfall times 100. Check, check, check. We nailed it, okay? 95 to 99%. We exceeded our 90%. We have a little ways to go. You could intensify, and we think we're still okay with this technology. Did we filter at least 75% of the water quality volume? And here I used this calculation. I divided the underdrain runoff by the total of the underdrain and flume runoff multiplied by 100. Check, check, check. 87 to 97%. That exceeds the 75% WQV threshold that we have as the standard. The last one, did we reduce the annual TP load by the MEP? And everything I found suggested for bioswales, we should be in the 50 to 75% range to be successful, to have achieved our goal. Here's the calculation. We're comparing the load from the grass swale with the bioswale. And that should be TP in the denominator there, the grass swale. For delta kappa, check, 66% reduction. But for the omega and epsilon bioswales, I have a question mark. Why do I have a question mark? Well, this calculation assumes that the grass swale did nothing, that there was no attenuative capacity or reduction capacity associated with those abandoned swales. And I don't know that that's the truth. We can't say. So if they did, then it's conceivable that these reductions would be even higher and consistent with having achieved our objective. Okay, so key points. The paired mini catchment design can quantify differences in pathways and treatment effectiveness. The major hydrologic differences we found were soil infiltration capacity, overland runoff, under drainage, and possibly local groundwater recharge under those bioswales. Greater abstraction and detention of highway stormwater runoff were not consistently achieved with the present design, however. You remember the difference we saw across the three pairs? We think the major weakness is a hyper-efficient underdrain system. It's just too efficient. It just works too well. We don't need it to work that well. We'd be better backing off of that efficiency. The bioswales, as we said, reduced the phosphate EMCs, but we found no reductions in N or TSM. We found evidence of trace metal leaching. And the synoptic stormwater sampling, while really not a great thing to do, honestly, safety-wise, could really provide some useful information for evaluating swale performance across an entire community or perhaps an entire corridor of highway as we did it here. And just something to provoke you maybe, this is a Chesapeake Stormwater Network, is bioretention an aspirational goal, but a misnomer? What did we see of any bio retaining anything? We do not believe there was retention. We think there was some biosourcing of nitrogen, but we believe the phosphate retention was sorption, chemical sorption. There's no bio in that. So why do we call these bioretentions? That'll get some questions going, won't it? If anything will. So that's it. I apologize. I think I'm 5 minutes long, Missy, but have at me, so to speak.
That was fantastic, Keith. Thank you so much. What I'm going to do now is I'm going to stop our recording, but we are going to get to some of our questions. So if anybody needs to drop off, that's